Start with a blank plane and a single point pinned at the very center, the origin. From here, we're going to grow arrows. Here are two of them, reaching off in different directions. And now the two questions this whole lesson turns on. First, by stretching and adding these arrows, can we reach every single point in the plane? And second, is either arrow redundant in the sense that we could already build it out of the other one? Answering those two carefully gives us four of the most important words in all of linear algebra: independence, span, basis, and dimension. And every one of them grows from a single idea: the linear combination. A linear combination is nothing fancy. Take some vectors, scale each one by a number, and add the results up. That's it. The scaling numbers, C1, C2, and so on, are called scalars. Slide them to anything you like, and you sweep out every arrow this recipe can produce. Make it concrete. Let V1 be 2, 0, and V2 be 0, 1. Now form 2 times V1 plus 3 times V2. Stretch V1 to 4, 0, stretch V2 to 0, 3, and add. You land on the point 4, 3. Different scalars would land you somewhere else entirely. Here is the sharp test for redundancy, and it's beautifully simple. Set a linear combination of your vectors equal to the 0 vector and ask one thing. Can the 0 vector be built only the boring way? Every scalar equal to 0? If that trivial choice is the one and only solution, the vectors are linearly independent. Not one of them is redundant. But if there's any other way, some scalar that isn't 0, and the sum still collapses to 0, then the vectors are linearly dependent. That non-trivial recipe is a receipt proving one vector was hiding inside the others. Watch what dependence looks like. Take 1, 2 and 2, 4. The second arrow is just double the first. So both lie flat along the very same line. U2 equals to U1, pure redundancy. Rearranged to U1 minus U2 hits exactly 0, with scalars 2 and minus 1. Neither is 0. So this pair is dependent, and together they reach nothing more than a single line. Now lift the same idea into 3 dimensions, where it becomes vivid. Here is space, with its 3 axes. Grow 3 arrows, U1 along x, U2 along y, and a third one, U3, poking out to 1, 1, 0. They look like they reach into space, but they don't. Every one of them sits flat on the floor, the plane where the height z is 0. They are trapped in 2 dimensions, and here is exactly why. Slide U2 so it starts at the tip of U1, and it reaches the head of U3. In other words, U3 is precisely U1 plus U2, the diagonal of their parallelogram. So U3 carries no new direction. It's dependent, and no matter how you scale these 3, you will never once leave the floor. 3 vectors, but only a flat plane's worth of reach. That reach has a name. The span of a set of vectors is the collection of every linear combination you can form from them. Every point you can possibly reach. One non-zero arrow, scaled every which way, sweeps out a single line through the origin. 2 arrows pointing genuinely different ways fill in a whole flat plane, and 3 arrows, each reaching into a truly new direction, sweep out all of 3-dimensional space. Put those 2 ideas together and you get the star of the show, a basis. A basis is a set that does 2 jobs at once. It is linearly independent, so nothing in it is wasted, and it spans the whole space, so nothing is missing. It's the Goldilocks set. Not too few arrows to reach everywhere. Not too many so that some become redundant. Just enough. Exactly enough. Here is the cleanest basis of all, for 3-dimensional space. 1 arrow along each axis, even, E2, E3. They are independent. None lies in the plane of the other 2. And this time, the third genuinely lifts up off the floor. And because that third arrow escapes the plane, their combinations fill the entire room. Any point you name, pick this one, is some blend of the three. That is what spanning all of space looks like. And that count, the number of arrows in a basis, is the dimension of the space. Every basis of a given space has the very same size, which is what makes dimension a solid, well-defined number. The plane needs 2 arrows, so its dimension is 2. Space needs 3, so its dimension is 3. Simple as that. There's a lovely counting rule that saves a lot of work. In a space of dimension n, the number of vectors alone often settles the question before you compute anything. If you're handed more than n vectors, they must be dependent. There simply isn't room for that many independent directions. Cram 4 arrows into 3-dimensional space, and at least one is always redundant. And going the other way, if you have exactly n vectors and they're independent, that's automatically a basis. You don't even need to check spanning separately. The count guarantees it. See it in the plane, which is 2-dimensional. 2 arrows already reach everywhere. So the moment you add a third, it has to be some blend of the first 2. Here that blue arrow is 8/10 of the gold plus 6/10 of the rose. 3 vectors in a 2-dimensional plane can never all be independent. Too many arrows, guaranteed redundancy. Let's turn the crank on a real example in the plane. Test the pair 1, 0 and 1, 1. Set a combination to 0 and read it off coordinate by coordinate. The first coordinate gives C1 plus C2 equals 0. The second coordinate, all by itself, gives C2 equals 0. C2 is 0, and feeding that back makes C1 0 too. Only the trivial solution survives, so this pair is independent. And since the plane is two-dimensional, any 2 independent vectors are automatically a basis. This pair is a basis of the plane. Now a pair that fails. Take 1, 2 and 2, 4. Set the combination to 0, and the 2 coordinates give C1 plus 2C2 equals 0 and 2C1 plus 4C2 equals 0. But the second equation is just twice the first. It says nothing new. So there are endless solutions. Take C2 equal to 1 and C1 comes out at minus 2. A non-trivial recipe hits 0. So the pair is dependent and their span is only a line. Let's step up to 3 vectors in space. 1, 0, 0, 1, 1, 0, and 1, 1, 1. Are they independent? And do they form a basis? Set the combination to 0 and split it into 3 coordinate equations. The first coordinate gives C1 plus C2 plus C3. The second gives C2 plus C3. And the third gives simply C3. This shape is a gift. It's already triangular, so we just back substitute. The bottom equation forces C3 to 0. Push that up. C2 must be 0. Push again. C1 is 0 as well. Every scalar is forced to 0. Only the trivial solution. So the 3 are independent. And 3 independent vectors in 3-dimensional space are a basis. Equivalently, stack them as columns and the determinant is 1, safely non-zero. Your turn now. Here are 3 vectors in space. Pause the video, set up the test, and decide for yourself whether they're independent. I'll wait right here. Here's the reveal. Look closely. U1 minus U2 is 1, 0 minus 1, which is exactly U3. The third vector was hiding inside the first 2 all along. So U1 minus U2 minus U3 collapses to 0. With scalars 1, minus 1, minus 1, none of them 0. That's a non-trivial recipe, so the 3 are dependent. Their span is only a plane, not all of space. If you caught that, you've truly got it. Trap 1. Spanning is not the same as being a basis. A set can reach the whole space and still carry redundancy. To be a basis, it must span and be independent. Both. Trap 2. Don't confuse independence with being perpendicular. Perpendicular vectors are always independent, but independent vectors need not be perpendicular. 1, 0 and 1. 1 are independent yet not at a right angle. Trap 3. The 0 vector poisons everything. Any set that includes it is automatically dependent, because you can scale that 0 by anything and add nothing. A non-trivial recipe for free. Trap 4. The determinant shortcut only works when you have exactly as many vectors as the dimension stacked into a square matrix. With more or fewer, the determinant simply doesn't apply. Let's lock it all in. Vectors are independent when only the all-zero recipe gives the zero vector. Nothing redundant. The span is everything those vectors can reach. Every linear combination they can build. A basis marries the two, independent and spanning the whole space. The just enough set. And the dimension is simply how many arrows a basis holds. Hold those 4 lines in your head, and independence, span, basis, and dimension will never tangle you up again.